So I'm going to give a progress report on a joint project with Ariane Jarampeika, Christian Lehn, and Marco Marcolan. So the ultimate goal is to prove big monodromy theorems on abelian varieties using techniques from D modules and perverse sheaves. So the motivation for this is the following setup. So we start with an abelian variety over C. So a complex vector space modulo a lattice, a dimension of A is bigger than 1. And we look at families of subvarieties in there. So this means you take, say, inside the product A times S over S. You look at the family subvarieties, which is varying. And we assume this to be smooth. And then we want to understand, ideally, we would like to understand the monodromy of these things. So we would look at the Gauss-Martin connection for this fibration. So of course, in this generality, you can't expect anything because the family may be non-generic. Nobody tells you that we are talking about a universal family. So this is far too special, but we want to look at not this monodromy, but actually at a twisted monodromy. So this is appeared in a paper by Lawrence and Sevin in relation with the Ravage conjecture. So the idea is, instead of looking at this family, you could pass to finite covers, and then if you express terms in things in terms of the variety y, passing to a finite cover means that you replace the constant sheaf on y by the sum of twists by torsion local systems. So we twist by a local system of rank 1. On the abelian variety, and so we look at the Gauss-Martin connection for this thing. So we get the local system, now taking the constant local system and tensor by L, and then taking push forward. Okay, and this you can do in any degree, of course. And you can look at fibers over a point in here. So maybe here I have a small one S, and let me call it Roman Y. The fiber over that point. So the fiber, of course, is then just the cohomology of Y with coefficients in L. So by L, I mean the restriction of L to the subvariety Y. So this only depends on Roman Y and Roman L. And of course, I don't want to do this for all L, but I'm interested actually in taking here a generic local system in the sense of generic vanishing. So a local system outside some finite union of translates of linear subvariety, character variety. Because then we know that the only n, so the only degree where possibly you have something non-zero here is the dimension of Y. Okay, so that's the setup. And so here I look at the fiber over a general point, which will be fixed from now on. And on this vector space, BYL, I now have two groups acting. One of the two is we call it M, which depends now on the family, only Y and L. So this is algebraic monodromy. So this is, you take the monodromy representation of this local system, curly V, and then you take the risky closure of the image of the fundamental group. So this is a subgroup of GLV, but there's also another group in here, And this depends only on the special fiber Roman Y. And this is the group I want to discuss today. So that's the group which is associated to the intersection complex on the special fiber. The intersection complex of Y, and then twisted by this local system L. So both of them, as I've written here, fit inside the general linear group. And the motivation for what I'm going to discuss now is an approach by an observation by Lawrence in 7. In their paper on the Ravage conjecture, they observed that there's a close relation between these two groups. So if you want to show the algebraic monodromy to be big, it's enough to show that this Tanakian group is big. And you will get that the algebraic monodromy is big for free. So the statement is the following. So assume that this Tanakian group is big in the sense that it's simple modulo its center and its representation on this space VYL is irreducible. And of course, there's one trivial case to be ruled out. You don't want Y to be a trivial family. So the family is not trivial, then of course you can take a trivial family, then the monodromy will be trivial and you don't know anything about the Tanakian group. But apart from that case, what happens is that if you look at this Tanakian group, then it's actually contained as a normal subgroup inside the algebraic monodromy of the family. So you should think of this maybe a bit like the theorem of the fixed part in Hodge theory, where you have a monodromy group and you have a Mumford-Tate group. The monodromy is really depending on the family, and the Mumford-Tate group is the Mumford-Tate group of the Hodge structure on a very general fiber. The situation is very similar here, philosophically speaking at least. So, I mean, for the theorem of the fixed part, the inclusion would go the other way around, but philosophy is very similar. So invariant tensors under the Mumford-Tate are monodromy invariants, and here the situation is invariance under the Tanaka group will give you monodromy invariance and vice versa. There's a small fine print, like also for the theorem of the fixed part. There might be issues with connected components and also with non-semi-simple groups. So this here really holds if you replace G by the connected component and then take its derived group, the commutator sub. And the statement is true in the nose. So the monodromy might, so this one might be disconnected, but yes? Well, Y is smooth and the morphism is smooth, but well, that's just notation, of course. This is not about singularities. So my motivation for looking at these groups in the first place was for a singular Y. But this whole talk will be about smooth subvarieties. So this is just notation. You can take the constant sheaf and shift by the dimension. Okay, so this is the statement. And the question now is how do you show these groups here are big in the sense that the assumptions here are satisfied, and ideally you would like G to be a classical group acting via its standard representation. And this is the first result. I want to mention here. So if y, okay, I should say, so this was the motivation, starting from a family and taking a very general fiber. Everything I will discuss from now on is a statement about these Tanaka groups, whose definition I will recall in a minute. And so everything from now on is a statement about a single subvariety in the abelian variety. So you can forget about families. Now it's no longer a relative story. It's an absolute story. So you take an abelian variety, you take a smooth subvariety, irreducible, and say it's a complete intersection of ample divisors. So you assume that the dimension is at least 2. Some more curves have to be treated by hand differently. And then you assume that the stabilizer of y is trivial. So the stabilizer is a subgroup of points such that if you translate the subvariety by this point, you again get the same subvariety. So this just says that y is not stable under any translation on the abelian variety. Okay, and then the statement is, so for very general L as before, this group GYL is, well, conceptually you would just say it's a simple group acting via a minuscule representation, but I will spell out what this means in practice. It's a special linear, special orthogonal, or symplectic group acting on the standard representation. That's the case I would refer to as being big. So that's the group you want for the application in the Ravage conjecture, for instance. And then there's one other case, which is what I will be discussing today. So you can have SLN, but acting not in the standard representation, but in a wedge power. I mean, for this to be really a new case, I should, of course, have not the first wedge power. And then also by duality, it's enough to go up to n over 2. And if you look at this action, of course, this is supposed to be VYL in this case again. By definition, this group will embed inside VYL. So here you have a kernel. So there's some subgroup of roots of unity. So that's the second case, wedge powers. And then you have a few exotic cases. So you have spin representations, and you have E6, and you have E7. And these are exotic, and they only occur in very special dimensions. So either you have a power of 2 for the spin representations, or you have the fundamental representations of dimension 27 for E6, or 56 for E7. So today I won't talk about this case C. This is kind of an exotic case. This one, I should mention, this one does occur for intermediate Jacobians of cubic threefold. So it's not like these cases don't appear in nature. But in any case, this only happens for dimension 27. For the other two cases, we don't know. So I don't know a single example of a smooth subvariety realizing E7 or the spin group. So this is still open. But I should say the dimension here is the topological Euler characteristic of your subvariety. So as long as your topological Euler characteristic happens not to be a power of 2 and not one of these two numbers, this case C doesn't exist. Whereas in case B, there are plenty of binomial coefficients, so it's too rough to exclude this just by numerics. Yes, it's the Fano surface. Yeah, that's the adjoint of this. So don't ask me well, that's the dimension. The dimension is of course, the dimension of the Lie algebra of E6. But this is the adjoint representation. And the way to show this is you compute the group for the Fanus surface, and then you realize that the theta divisor is, well, essentially the surface times its dual, which gives you the adjoint representation. So that's the way to see the theta divisor in there. Of E6, you mean, or for all of them? No, I mean, so those cases appear, those you will see in a minute, those appear for Jacobians. This E6 appears for intermediate Jacobians, and my guess would be in all the other cases for theta divisors, you only see the big ones in case A. But it's not clear, and in fact, yeah, the situation may be richer, because if you allow singularities, I mean, so for smooth theta divisors we are in this case, but for singularities, if you have bad singularities, this no longer applies, because this is for smooth subvariety. So this is a big open thing. I mean, in small genus you can compute everything, like genus up to genus 4, it's fine, and genus 5 already we only know top Andreotti-Meyer strata, but if you go deeper in the stratification, it's unclear. A priori you could have almost anything. But even in the smooth case, there's something interesting going on. This is what I want to discuss today. So before starting this, a remark. So this is ongoing work with the 3 co-authors I mentioned above. In the case of hypersurfaces, this was known already. So for hypersurfaces, I mean smooth hypersurfaces, in the case of symmetric theta divisors, I observed this a couple of years ago, and then Lawrence and Savon in their preprint extended this to non-symmetric hypersurfaces. So this was kind of easy. But what was less easy is to rule out these 2 cases. And okay, to avoid making false statements, let's assume G is bigger than 3, otherwise some numerical exceptions to their list. Okay, case C was trivial for them, because if you have a smooth hypersurface, then the Euler characteristic is divisible by G factorial, so it will never be a power of 2, and it will also never be one of those 2 numbers. So case C was no problem, but this case B actually not easy. So in their preprint, this takes around 26 pages of combinatorics. And it's really combinatorics. So the condition of having a wedge power gives them some restriction on Hodge numbers. But after they have this restriction, they do combinatorics of Euler numbers, really pure combinatorics, and it's 26 pages. And then they have some Python code as well to verify what's not in those 26 pages. So it's ingenious, but extremely technical. And when you try to generalize to higher codimension, it's hard to say how you would do this. And so today, I want to talk not about this case, where we don't know how to do it in a better way, but I want to talk kind of the opposite direction. So this is the smallest possible codimension, codimension 1. And we are at the other side, small dimension, so high codimension. So, and high codimension now means currently the threshold is half the dimension plus minus 1. So G minus 1 over 2. In that range, I mean, for Y as in theorem A here, smooth, irreducible, and so on, this case B occurs if and only if there is a smooth curve C inside A such that if you look at the symmetric power, so I call this K here, sim KC, then you have a sum map, the sum of K copies of the curve inside A. And so this here is an isomorphism, and this sum is actually equal to Y. And again, this, of course, this can happen, but it happens not so often. I mean, but it happens, for instance, if A is the Jacobian of a smooth curve C, and this being an isomorphism means that you should have no linear series GK1. So for instance, for K equals 2, the curve should be non-hyperelliptic, then the sum here will be smooth, and so on. So basically this says, yes, wedge powers do occur, but only in the obvious case. Yes? Yes? Yeah, for curves you can do all of them. And basically, I mean, the situation is the same. I mean, for curves, the point is, for curves, you first do the curve itself, and you see SL2G minus 2. And then the WDs are just the wedge powers of the curve. So this statement here, I've said you want no GK1. This is just because in our assumptions on Y, we put that Y should be smooth. But the picture for the wedge powers extends also in the singular case. So, yeah, definitely. So the Carnot surface is distinguished by this group. Okay, so this is all I wanted to say for the statement. And now I want to discuss a little bit of the proof. So the idea is, instead of doing combinatorics, trying to do geometry. So first we pass from group representations to characteristic cycles of perverse sheaf, and then we do some conormal geometry to understand these characteristic cycles for wedge powers. So let me just recall how you get these Tanakian groups for perverse sheaves. So you take a perverse sheaf and you take a generic rank 1 local system on A. Then we know that the cohomology of P tensored by L is 0 in all degrees. Different from 0. So let me call this maybe PL. So I mean, this is an old result by Weiser and myself, and also by Christian Schnell in a D-module setting, and in a more topological setting using the Melian transform. This was reproved by Bud, Schnell, and Scholze in 2018, I think. Okay, so we have this, and this means that after you tensor by generic rank 1 line local system here, the H0 will become an exact functor in any finally generated category. So this is useful. And now we start with this perverse sheaf PL, and then we take the category generated by it. The abelian tensor category generated by this perverse sheaf. And when I say tensor category, I should tell you what the tensor product is. And the tensor product here is the convolution product, which is defined as follows. If you have two perverse sheaves, P and Q, then their convolution is defined as follows. You take the external tensor product on A times A. So this lives on A times A, and then here you have the sum map to A, and you just push forward under this sum map. And so abelian tensor category generated by this means you take all the convolution powers of PL and all the subquotients and all their duals. And this category turns out to be very nice. So it's actually what's called a neutral Tanakian category. So it's a tensor category which is equivalent to a representation category of some algebraic group. And that's the Tanaka groups I was talking about before. So this is like the characterization of Mumford-Tate groups you may have seen in terms of no, it's used on the blackboard, which I needed to clean first. So this was just some comment as a reminder, but it's used now because I said before this is a neutral Tanaka category. So this PL here. And you know, to have a neutral Tanaka category, you need a fiber functor to vector spaces. And for this, now we can take this H0, because it's exact by this vanishing theorem if you choose L generically. And then this says that this one here will be equivalent to the representation category of some algebraic group, such that this one here is just the forget functor. And the G is G of PL. We want is the automorphisms of this fiber functor. Or omega here. It's not completely obvious, but you can check. So you have to check various things. I mean, and I've been cheating all the time because, I mean, I didn't really tell you the definition. I just said tensor category generated by, but I didn't tell you the ambient category. It's not perverse sheaves, but it's a quotient of the category of perverse sheaves. You have to mod out, for instance, all local systems. And more generally, any perverse sheaf that comes by pullback from an abelian quotient variety, you have to mod out. A different way of saying this is the perverse sheaves which have Euler characteristic 0 have to be modded out, or yet another way of saying this, those which for which generic vanishing actually gives you generically 0. So those disappear in this quotient category. And after you do this quotient, the functor becomes faithful. Okay. And the remark here is this G. I mean, if you start with a semi-simple perverse sheaf, like a perverse intersection complex, then this group here, G, is reductive just because the category will be semi-simple abelian by the decomposition theorem. And okay, so, and also I should say this, this group here does not really depend on the twist L. I mean, they are all non-canonically isomorphic. It's just if you want to write down a specific model, you have to fix a specific L. Okay, so if you have a reductive group, then its representation category is really governed by the combinatorics of highest weights for a maximal torus. And this one is completely captured by the representation ring of the group, which is the Grothendieck ring of its representation category. The Grothendieck ring means for direct sums and tensor products. Okay, and so far we haven't seen any cycles. But now you can, I mean, basically take any additive invariant on the category of perverse sheaves and you will get an invariant on the Grothendieck ring. And this you can use to get information about this representation ring. And so I want to do this for the characteristic cycle of a perverse sheaf. So recall, I mean, this is by definition the Grothendieck ring of a certain category of perverse sheaves. And then on perverse sheaves, I can apply characteristic cycle to go to the group of Lagrangian cycles in the cotangent bundle. So if you want, this is a free group generated by the conormal varieties the subvarieties of A. And these conormal varieties I want to take in the projectivized cotangent bundle. So this is a trivial bundle. Let me write it just as A times P. So here, if you have a perverse sheaf Q, you send it to the characteristic cycle of Q. And now there's a small, again, a small technical fine print here. I said already before, for this technically to define these Tanakian categories, you mod out by all perverse sheaves that come by pullback from an abelian quotient variety, which means you mod out by all things whose support is kind of fibered in abelian subvariety if you want. And so this means here you should kind of mod out by all those subvarieties which are fibered in abelian subvarieties. So what's left then are those which are of general type. So this is why I'm writing a small cc here. I would use the classical characteristic cycle. I would denote by capital CC as usual, and the small cc is supposed to remind you that it's a slightly different thing. I discard everything which is supported on subvarieties that are not of general type. And being of general type is the same as the following. I mean, if you have your Z, you have a Gauss map, which is defined as follows. You take lambda Z, this sits inside A times P, and then you project to the cotangent space P. And being of general type is the same as this map being generically finite. So for dimension reasons, it's then also dominant. So it's a generically étale cover. Okay, and what makes life now easy for us to compute with these cycles. This CC is actually a homomorphism of rings when this L of A is endowed with a ring structure which essentially, so if you have two conormal cycles, lambda 1 and lambda 2 in this group, then what you can do is, I mean, both of them live inside A times P. You can take the fiber product over P. So you take the fiber product of the two Gauss maps, and then you push forward under the sum map. So this one here lives inside A times P, and then you push forward under the sum map, which makes these two A times A into a single A. Okay, and this push forward is done in the sense of cycles. So whenever you have here a component on which the sum map is not generically finite, then the push forward is declared to be 0. Okay, I want to discuss today not products, but actually wedge powers. So actually you can upgrade this to homomorphism not of rings, but of lambda rings, which is precisely what you get when you take the Grothendieck ring of a tensor category. So for this I have to tell you how to do wedge powers. And to avoid too many capital and small lambdas simultaneously, I call these lambda operations alt k, not lambda k. And so what you do here is, well, you take now a k-fold fiber product. In there you have the diagonal, so the big diagonal where any two of the components are equal. You take out this one, and okay, then you take the risky closure again, and then you push forward under the sum map. And now there's one correction I have to make. Here you have an obvious action of the symmetric group Sk. And so here this is divisible by k factorial. So I reduce it by dividing by k factorial. And so this is what the wedge powers do geometrically. And should speed up. So the example is, for simplicity, let me say C is non-hyperelliptic curve. And you embed it inside its Jacobian. Then the wedge powers of the conormal variety to C are, well, they come in two types. You see the WD. If D is at most G minus 1, but then, of course, so sums of copies of C. And then starting from the degree being G or higher, you see, well, a translate of minus WD. 2G minus 2 minus D. So you see in a certain range, the dimension down here goes up, but then it goes down again. And somehow the point of our result is to pick a certain range where you can make sure that the dimension actually grows linearly with D, like in this example. So this is the this is somehow the second ingredient. So for curves, everything is easy because you can understand the sum map explicitly in terms of Noether theory. But now when we start with the situation where you have an abstract subvariety Y and you know that it's a wedge power, even if you know it's a wedge power of something, you don't know of which something. And so somehow we want to show that if a smooth subvariety y is a wedge power of something, then that something, whatever it is, behaves like in this example. So that's somehow the point of this talk. And so the first problem is how to control, if you take wedge powers of a subvariety, how to control the dimensions that you get here downstairs when you project down on the abelian variety. And for this, so you take such a, say, conormal variety inside this projective bundle. The idea is to look at segregate classes. So this lambda is a cone, if you want, in the non-projectivized cotangent bundle, and for a cone in A times a vector space, you can make sense of segregate classes by taking intersections basically with linear subspaces of P here, pulled back to A times P. And so I write the total segregate class here as the sum of terms, and this now goes inside the showering of A. But I've stopped at G minus 1 here because I've projectivized here. So the last bit in dimension G would be the 0 section inside A times P, but that one I've inside A times the vector space, but the 0 section I've discarded because I needed to projectivize. Which is again the same reason. I mean, in this quotient category, I've divided out by local systems. For local systems, the characteristic cycle would be the 0 section. So for the same reason that I needed to mod out something upstairs there, I also have to take not the full showering, but the truncated showering. So this is the full showering modulo the ideal in the last dimension. And this is now well behaved. So we have passed from representations to cycles. And the next step is to pass from cycles to actually segregate classes of cycles. And then the idea is simply to read off the dimension of the supports of these conormal varieties by looking at vanishing or non-vanishing of segregate classes. Of course, for this, we have to be able to compute segregate classes not just for a single conormal variety, but for wedge powers of conormal varieties. And this looks a bit hard at first sight. But at least for convolution products, it's easy to compute them in nice cases. And fortunately, our assumptions on Y guarantee that we are in this nice case. So what we get, these segregate classes are additive, so they give a group homomorphism from this group of Lagrangian cycles to the showering, truncated in degree G minus 1. And the bad news is this is not a ring homomorphism. Well, here, okay, this one is a ring, where the product is the Pontryagin product on Chow, which is defined like the convolution product. We take the external product of cycles and then push forward under the sum map. This defines a ring structure, and what I've divided out there is an ideal, so the quotient is again a ring. But the segregate class is not a ring homomorphism because you have excess intersections in fiber products in unfortunate cases. But the good case is if you don't look at all of Lagrangian cycles, but only on those. I mean, a cycle here is the sum of certain conormal varieties lambda z, and you only take those where this Gauss map here is finite. Not generically finite. I mean, upstairs, when we restrict it to general type things, we say generically finite Gauss map, but here we really take those whose Gauss map is finite as morphism, finite morphism. And the statement is this here. It's not just a subgroup, but it's a subring. And the total segregate class restricts on this subring to a ring homomorphism. So whenever you have something whose Gauss map is a finite morphism, you can compute convolution powers and then take their segregate classes, and that's the same as first taking segregate classes and then taking von-Triagen product. And the advantage is convolution powers are complicated because you need this strange fiber product up there, which is complicated conormal geometry. Von-Triagen product is something you can compute rather easily. And so what you get out of this, if you have two subvarieties in A, such that the Gauss maps of both are actually finite, so the conormal varieties are in this subring of where you can compute things nicely, and you put D to be the minimum of the dimension of y, sorry, the dimension of x plus the dimension of y, and G minus 1. Then, if you look at the segregate class of the product of these two conormal varieties, and if you look at the degree E piece, degree I piece, sorry, this is an effective cycle and a non-zero effective cycle for all degrees from 0 up to D, and it's 0 for all other I. So that means if you take a convolution product of two things and you take this segregate class, then it behaves as expected. The dimensions add up to dim x plus dim y, unless you reach the boundary case where the sum would be G minus 1 or higher, and then kind of things stop. And if you think of what I still have on the right-hand side blackboard, you see that this stopping at a certain point is natural. So this will happen. So this is not an artifact of the argument, it's really needed, this truncation at G minus 1. For all which I'm considering today, is the short answer. So for instance, for a complete intersection of ample divisors, finite, if it's a smooth complete intersection. Or another, instance, if you have a smooth if you have an ample divisor, then any positive dimensional fiber of the Gauss map must meet the singular locus, for instance, and so on. So it's in many cases it's a finite morphism, but of course there are also plenty of cases where it's not finite. And then you have to be more careful with the intersection theory that goes into this proposition. So what saves the day is that for our case, where y is a smooth complete intersection of ample divisors, we do know that the Gauss maps are finite. And then we can compute things. Okay, so maybe I don't explain this. So the point is really that the von-Triagen product behaves nicely when you have finite Gauss maps. And then the next step, before I come to an end, this is really the final piece. So suppose you have a subvariety Z in A, such that the Gauss map is actually a finite morphism. And let's call its degree n. And now we look at dz of I is the dimension of, well, you take the ith wedge power of the conormal variety and then you project down to the abelian variety. So the wedge powers live in A times P and you project down to A. So in this curve example, the dz of I would be, if you take z to be the curve, it's, well, dz of I would be I for I at most g minus 1, and then it would go down again. So that's the dimensions we want to control. And what we get is, if there exists an index r such that dz of r is less than g minus 1 over 2, so this r here would be the wedge power which we have in the theorem B. And, well, this r should be at most n over 2. I mean, as usual, we are only going up to the middle wedge power, like in the case up there as well. Then this function dz from 1 up to r going to n is non-decreasing. So the situation is precisely as in this this curve example. And then from this you deduce that r times the dimension of z is less than g. And then from this you actually deduce everything. So I think I should, I don't know, maybe I can very briefly say the key idea of this proposition and then stop. Or should I stop immediately? No. So the idea is here, you can really essentially this is linear algebra. So there's nothing deep going into this. Which seems to indicate that in general this is a good construction for maybe approaching also higher dimensional cases with a better control on sacred classes. So, I mean, I only show you part A. Part B is then easy consequence. And the idea is just to use descending induction on R. So you look at the ith wedge power, and you take its product with the dual, which is the wedge power of lambda z, lambda minus z. And then, just by, in terms of linear algebra, if you want, if you have wedge I, tensor wedge I of the dual vector space, you know that the construction for I minus 1 will embed inside the one for I. And that's a trivial observation, but okay, so maybe these were cycles before, so maybe here I want to write support. And of course, for this to work, you should not exceed the middle dimension, otherwise you have a problem. But in the middle dimension, it's fine. And then you see that because these are all pure dimensional cycles, they are conormal cycles, if one is included in the other, it's a sum of components, except that maybe the multiplicities don't match, but we don't really care about the multiplicities. So what we get is lambda I is alpha times alpha I minus 1 plus an effective cycle for some maybe rational but positive alpha. And now we win because then we take the total segregate class on both sides, and you see that the segregate class of lambda I is bounded below by the segregate class of lambda I minus 1 in the sense that the difference is an effective cycle. And now this one here is non-zero only in degrees, at most twice d of I, which by assumption is less than g minus 1. Whereas the right-hand side here is non-zero in all degrees, at most the maximum of 2d of I g minus 1 by this previous corollary. And then you just compare those two bounds. You have something non-zero in all degrees up to the maximum of 2di and g minus 1. But on the left-hand side, it vanishes in all degrees above 2d of I, which is less than g minus 1. And then I'm finished, except that, of course, here you want to write I minus 1. Then I'm really finished. Okay, so that's the idea. And then once you have this, yeah, there would be another page of explaining how to deduce the theorem B, but I think the key geometry has happened. So basically from this statement in B, you deduce that the support of the wedge power is really a sum of copies of Z. And then you need to work a little bit more to make sure that Z is actually smooth and is actually a curve. And for this you need that. Well, first you show that the morphism from the symmetric power of Z onto Y is an isomorphism, and then you know that symmetric powers of something are smooth only if the something was a smooth curve. And that's basically the end of the story. So I think I should stop here.
So I would like now to invite questions to this very interesting talk, and remember, ask for the microphone. Don't be scared.
Curious how you deduce theorem A from this picture.
No, I don't.
Okay, or what's involved?
So actually, yeah, theorem A was the first step, but I wanted to talk about something new, so I decided to discuss theorem B. Theorem A also uses this conormal geometry, but the idea behind this, if you have a, I mean, roughly, you have these Tanakian groups, and if you have, well, say up to isogeny, you can assume if the group is not simple, then it would be a product of two groups. But then, okay, I mean, if you want, you can take the intersection complex of Y here, and then tensor by L. And this now acts on the VYL. But okay, this one is an irreducible representation of that group, but irreducible representations of products are tensor products of irreducible representations of the factors. Okay, so this is an identity in the representation ring. And now you apply this CC to conic Lagrangian cycles. You get an identity which tells you that the characteristic cycle of this intersection complex, well, twisting by L doesn't change, of course. This is actually a product of two cycles. And now, when I define this product of cycles, I said this is the involves you do a fiber product and then you do a push forward under the sum morphism. This really push forward on cycles. If you have a fiber product and you map it down and it has a certain generic degree, you multiply the cycle by the generic degree. But when Y is smooth, this is an integral cycle. So here, the multiplicity is 1. And this forces whatever you have here, the two cycles have to be integral as well. And this lambda y is actually equal to the convolution product in the strong sense that here you will get lambda 1 is lambda z1, lambda 2 is lambda z2, and the statement you get is if you take the fiber product and if you apply the sum morphism here, this is birational. Because otherwise you would have higher multiplicity in front. And then once you know this, well, this is almost as good as saying that y is a sum of z1 and z2, except that, of course, you have to work to make this true. But you can check under the assumptions which I wrote, for instance, if you assume you have a smooth, complete intersection of ample divisors, you will get this. So, I mean, this maps to a times a, and in fact, it maps to z1 times z2. But a priori, in here, you have something which might be smaller. And then this one here maps onto y. And then you have to control that actually here you will have equality, and then you can show that this doesn't actually happen. So this requires some extra work, but this is really conormal geometry you have to do. You can discuss afterwards if you want. So you really use positivity properties of the conormal varieties to exclude this case. And that, I mean, it's some piece of work you have to do, but it works very smoothly in this case. And this will tell you that the group cannot be a product of two groups. And then if you look closer, I mean, if you do this for after applying isogeny, this will tell you also the connected component cannot be a product. And then, of course, you know more, because this cycle here, I mean, this homomorphism here, if you look at what the representation ring actually is, you can take the character ring of a maximal torus and take the Weil group invariant elements. And then here, you have a basis consisting of Weil group orbits of characters. And this basis becomes mapped to a basis consisting of conormal varieties. So if you have here a conormal variety entering with multiplicity 1 and nothing else, this means that up here, you are forced to have a single Weil group orbit for your representation. And this means the representation is what's called minuscule. And then you are left with this finite list of cases I gave at the beginning. So that's roughly the argument.
Well, if not, then we thank the speaker again for a very interesting talk, I think.
Thanks.